this is Dr. S.P. Arsa from Mechanical and Industrial Department, IT Roorkee. I am going to deliver my lecture 16, and the course is like the strength of material, which is developed under the National Program on Technological Enhanced Learning. If we refresh those previous lectures, then we found that if a material is subjected by the tensile load, and if this material is having a composite bar kind of, if we have 2-3 different kinds of bars are there, and if they have the uniform cross section, but if they have the different like the area, as well as if they have the different modulus of elasticity, and if they have even like the different lengths altogether. But if we assume that if both the ends of the composite bar is sustained by the two supports, and if we apply the load, then we got this uniform extension, and we can say that the uniform strain is there, whatever the strains are. So, this kind of analysis which we have made in the previous lecture, and we found that if we assume that there is a deformation is same, then how it gives an impact on the different components of these bars, and how you see the deformation is taking place individually in these the components components of this composite bar is. So, then you see we found that actually how we can calculate the equivalent this Young's modulus of elasticity, because whatever the deformation is there under the application of this force is the elastic deformation, and if we apply the Hooke's law, then we can easily calculate the equivalent the Young's modulus of elasticity for a composite bar. And after analyzing those things, we found that if only external excitation is there, or we can say the external applied load is there, then we can simply compute that okay, this is the uniform strain is there, and since we have uniform strain, then how these stresses are there, these individual stresses are there in these individual components, and the individual areas are there, and how they are interacting to each other with this application of force and the stress versus strain. Then in the next case, we found that if we have a composite bar and the temperature is there, means if any effect of the temperatures are there, then we have again a kind of the normal stress known as the thermal stress. And then you see these thermal stresses are well set up that they are acting in the normal strain, like the normal way, like the tensile is there or the compression is there, because if you are raising the temperature, definitely is going to be extension in those bars, and we can simply compute as a thermal strain in a positive direction. And if you see like a kind of cooling is there, then definitely there going to be like the contraction is there, and we can say there is a negative thermal strain is there. Then how we can compute those kind of strains that we discussed in the previous bar. And then also if a bar is there and if it is subjected by normal pulling, and if the temperature effect is there, then what the interaction is there in between the thermal stresses with the normal stress component, and then how we can compute the equivalent part of these these two stress components, that kind of discussion which we made in the previous lecture. So, then we found that if we we have, let us say, the composite bar in which the two different the metals are there, like we have the steel bar which we discussed, and we have a brass tube, and if we apply the same temperature, this extension is absolutely depends on the linear thermal expansion of the coefficient, means we have a coefficient which has a linear expansion. So, it depends on and this alpha which we defined so called is absolutely a function of material. So, as we apply the temperature, since you see whatever the alpha is there, that means whatever the thermal coefficient is there, corresponding changes are there, or we can say the corresponding expansion is there at the free end of the bar, because if the composite bar is rigidly fixed up at these 2 points, then we can simply assume that there is a uniform deformation in that bar, or we can say simultaneously the uniform thermal strains are there in that bar. But since you see here, we are saying that if we have a cantilever kind of like the element in which one end is fixed, one end is free, and at the free end if we apply this kind of temperature variation, then definitely we are going to get the different expansions, or we can say the contraction for the different kind of material. So, in that if you want to make an equivalent kind of composite bar, then there is a kind of contraction in a material which is having a more or we can say high thermal this expansion, and there is an extension in the less thermal expansion. That means you see if you want to make the same this extension in both of the bar, even they have the the different thermal expansion, then you see we need to put or we can say there is an interactive effect is there from the shorter member on the higher member, and we can say the higher member on the shorter member. So you see, if a shorter member is there, then there is an extension. So there was you see, you know, like a kind of extension in the steel bar, and there was a contraction in the this brass bar was there, and then you see we made the equivalent you know, like the extension, and based on this equivalent extension we, you know, like formalize those things, and we found that if we have, you know, again we found that even if you see we have a different materials, and though they have, you see, you know, like the different alpha, that means the coefficient of linear expansion, apart from that also, if there is a composite bar, or we can say the compound bar, then we can get the uniform extension, and we can get the uniform thermal strain in that, or we can say whatever the this stress into the area is there, which is equals to the stress into area in the another way, or the stress into area divided by the Young's modulus of individual part will be equal to the stress into area divided by the Young's modulus of elasticity for that particular material. So the meaning is pretty simple, that if we are talking about a composite bar, then the things are pretty symmetrical, and if you want to calculate the individual parameter, then how they, you know, like how they can get, and how the you know, interaction is there in between these other parts of a bar under the application of either the temperature or the, you know, external applied load, this kind of discussion which we made in the previous lecture. So now in this lecture, you see, again we are gonna, you know, like continue the previous part, that you see now we have, you know, like the thin cylinder. Then how we can, you know, like calculate, because you see if we have, you know, like a kind of cylinder, then probably you see whenever we apply either the externally applied load or we have a temperature variation, then definitely there gonna be, you know, like the extension is there in the longitudinal direction, but what about the lateral direction? So there gonna be, you know, like contraction is there in the lateral direction. Then how we can, you know, like formulate that, means which pressure is dominating towards the axial direction and which pressure is dominating towards the circumferential direction. These, you know, like these are the two main factors on which we are going to concern, and then we are going to analyze those part. So here it is, you see, when we have a members which are subjected to a axisymmetrical loads, that means you see if we have a pressurized thin walled cylinder, we have a cylinder which has the wall of less thickness. So thin cylinders are there. So pressure vessels are excessively important in the industry, because you see everywhere you will find that the pressure vessels are there. Just even if you are talking about the boilers, or even if you are talking about to generate the pressures, always the big vessels are there, and those vessels, if you want to compute the thickness of the wall, you will find that they are very thin because they are, you know, like always playing in an axial way. So normally you see we are, you know, like going for the two types of pressure vessels in common industries. Like one is the cylindrical pressure, in which you see they have a cylindrical shape of a kind of vessels, and you see, you know, like those inside the pressures are either the pressures are being formed by the steam, or we can say, you know, like these are the different kinds of chemicals are there through which the pressure can be generated, and they are simply acting towards the x as well as the circumferential direction. And other thing is the spherical pressure vessels. So in the particular analysis of thin wall cylinder, which is subjected to an internal pressure because the steam generator or any kind, you see it is assumed, this is the big assumption is there in that particular thin wall cylinder analysis. It is assumed that the radial planes, whatever you see the radial planes are there on which this steam is, you know, like putting the pressure, remains radial, and the wall thickness does not change due to the internal pressure. That means you see there is not the stress concentrations are there all across this pressure vessel. So there is no change in, you know, like the thickness due to, you know, like the internal applied pressure. So thickness remains same, and also whatever the you know, like the radialness is there, whatever the all across the circumference, it remains its original shape due to the action of the internal pressure. So these, you see, the two big assumptions which we need to, you know, like put to analyze the pressure distribution, or we can say the stress, or we can say the strains in the thin wall cylinder. Then although the internal pressure acting on the wall causes the local compression, you know, like stresses, that means you see, you know, like always we have, due to, you know, like the internal pressure, always we have a different segments where these compressive and the tensile stresses are there, which is equal to pressure, because as I told you, the pressure is not only, you know, like this is the externally applied kind of force, because force per unit area it is there. So where the effective part is there on which these externally applied forces are there, this will give you the pressure. So you can say that whatever the local compressive stresses are coming at the different segments, they are always equal to pressure. And you see, even we have discussed that actually there is an analogy in between the pressure and the stress. Pressure is force per unit area, that is the Newton per meter square, or even it is the Pascal, and the stresses are also the same, pressure per unit area, or we can say Newton per meter square or the Pascal. But there is a difference. The difference is simply that the stresses are always being induced due to the application of force, while pressure can be applied. That means we cannot apply the stress. Stresses are always inducing in an object, while pressure is always applying on an object. So here you see, come to the main point, its value is negligible, because you see, like whatever the local compressive things are there, whatever the deformation due to these stresses, they are very small, or we can say we can simply neglect. They doesn't have, they don't have the real dominancy all across the body. Okay, so that's what we can simply compare those things, and hence the state of stress of an element for a thin walled like cylinder pressure vessel is considered to be biaxial one. That means, you see, as I told you, we can always go for the axial, that means whatever the longitudinal part is there, and this normal to that towards the circumferential part, that is, you see, this y direction. That means we have x direction, y direction, and these two biaxial stresses are always there in the thin walled cylinder, and these the stresses are always coming due to the internal pressure. Further, in the analysis of them of this particular cylinders are always, we need to be considered that what is the weight of the fluid is there inside that. If we are considering the weight, then again there has to be, you see, we need to consider what the dynamism is there. So we need to assume that whatever the weight is there, irrespective of whatever the the liquid or the steam or whatever, due to which the internal pressure is coming, we need to consider the negligible. So even if you are considering that the pressures are there, and these the pressures are acting all across the body, but you need to neglect those kind of weight, so that you see whatever the this stress formations are there, it has to be uniform all across the circumference of this thin pressure wall. So now you see, just consider a long cylinder, as you can see in this figure on your screen, of a circular cross section with an internal radius R2 and a constant wall thickness T is there. That means, you see, what we have this this cylinder is there, thin cylinder, which has a thickness T. So once you have the thickness T, and which has the diameter capital D is there, and the Z direction you can see here towards this direction, we have R, we have theta. So it is a Cartesian coordinate in which there are three main coordinates, R, theta and Z. So whatever the stress components are there, as you, if you just go previously, then you find that if we have the polar coordinates, then we have r theta z, and if we have the Cartesian coordinate, then we have the x y z. So if you have r theta z, then you can easily calculate the stress component at the oblique plane. That means, you see, the sigma theta like in the normal component, as well as you see in the shear component tau theta. So it's pretty simple, you see, to calculate the normal stress component and the shear stress component due to the combination of these this interactive part, like you see the sigma r, because it is always normal to these things. So always we have the normal stress component sigma r, sigma l is there. Sigma l is nothing but equals to towards the length of those things. So these are the sigma l directions. So what we have to, if we are talking about the the plane which is perpendicular to this particular cross sectional area. So if we are talking about this radius, then we have the sigma r towards this direction, we have the sigma this theta is there towards the circumferential direction, because this theta is there. So we have sigma r in this direction, we have sigma z, and we have sigma theta. So all three mutually perpendicular directions gives you the three kinds of stress formation here. But the key thing is that actually, since we are considering here the biaxial form of stress, then we have a thin cylinder. This is the T is very small in that, and this is the cylinder in which you see if the pressure is flowing all across this body, one, you see, due to this pressure there is always a kind of extension is there. So you see always we are considering that this body can be extended in the x direction, and then another part will come as the circumferential part, like in the theta. So in that, you see, you can say this sigma z and sigma theta will play a dominant role in those kind of thing, because both are the normal stress component, and since any fluid is flowing or any steam is there, it plays in forces it always offers and forces towards the circumference as well as the in the x direction. So you see, like this cylinder will give you a clear feeling about those things, that wall thickness is like the constant and it is very tiny. So always you see, like whatever the stresses are coming in the circumferential one, they are always dominating and they are depending on what the radius is there and the thickness is there, and what the load application, or we can say the force application is there from the steam side inside, like that. So the cylinder is subjected to a difference of hydrostatic pressure, like if I am saying that if it is P, so hydrostatic pressure P between the inner and the outer surfaces. So you see here we have the thickness. So the, if the inner surface if we are talking about and the outer surface we are talking about, then whatever the radius difference is there, that is the thickness. So if we are saying that the hydrostatic pressure is applying, so hydrostatic pressure is always applying uniformly all across the circumference of the body. So in many cases we can say that the P is between like the gauge pressure within the cylinder, like which we are always taking outside the pressure to the ambient. That means you see, whatever the, if you are talking about the pressure, then again I just want to refresh your concept that like whatever the datum pressure is there, that is the normal pressure, like, or we can say the atmospheric pressure is there. So one is the ambient pressure, which is the realistic pressure, which is always like greater than the atmospheric pressure, because atmospheric pressure plus gauge pressure will give you the absolute pressure, or atmospheric pressure minus vacuum pressure, whatever the vacuum is there, will give you the absolute pressure. So if you are talking about a general domain condition in which you see like it is open to atmosphere, then gauge pressure is the real applied pressure is there, because it is more than the atmospheric pressure, and like it will give you the clear feeling that since this gauge pressure is coming, these external forces are there due to this atmospheric pressure plus this we can say the gauge pressures are there. That means you see, whatever the ambient things are there, that means whatever the room temperatures are there, these pressures are always applicable. But if you are saying that there is some external source is there, that means, or we can say if there is an external excitation is there, it always comes through some more pressure, positive pressure, or technically we can say it is a gauge pressure. So you see, this is a pressure phenomena. If you are talking about any thin pressure cylinder, then always pressure, this gauge pressure is playing as a key role, because we are not going in the negative pressure like a vacuum pressure, always we are going for the positive pressure. So by thin walled cylinder means like that how much thickness is there, because as it is clearly stated that we are talking about the thin walled. So how thickness will vary and what the relation is there in between the thickness and the inner radius or outer radius, that we just want to like focus is. So here the thickness of this thin walled is very smaller than the radius Ri, or we can say that actually if you want to quantify those things, then we can easily quantify by the ratio of the thickness to the inner radius. So whatever the ratios are there and corresponding, you see like these values are, we are quantifying those things, and even this kind of like the tables are to be made based on that. Okay, now we have the T by Ri is 0.05, 0.1, 0.15, 0.2, 0.25, and like corresponding grades are there. So let us say if I want to make the thin cylinder of this nature, like let us say this T by Ri is 0.15, it has a like the specific nature and it has a specific applications altogether this. So if we are talking about the thin wall cylinder, then it has like somewhat a laser ratio in between the thickness to this inner radius. So here in this particular thing we can say that we are computing this T by Ri of the thickness of the radius, it should be less than 0.1. So if you are talking about 0.05 as I told you, or 0.75, or even 0.1, or even lesser than that, always they have a different kind of application. So and even we always try to keep whatever the internal pressures are there, so that there shouldn't be like the extension or the deformation is going on, it's going beyond a certain limit, or we can say a permanent set of deformation will be existing if we go certain like certain value of the load application. So an appropriate coordinate system, as we discussed, that actually the r theta z is to be taken, which can be easily described, because what we have taken here is a cylindrical like the pressure vessel. So again we have to choose the cylindrical polar coordinates like r theta z, which we have shown in the previous diagram, that you see in towards the r, and theta is towards the circumferential and z is towards the longitudinal part. So when I am talking about the r, then it is always normal to the plane concerned, And when we are talking about the theta, where you see all the circumferential or the different kind of stresses are to be occur due to the stress due to this pressure application. So here if I am talking about r theta z, then the z lies along with the axis of the cylinder, as I told you, towards the longitudinal direction. R is the radial towards the outside of the plane, and theta is the angular coordinate as usual, where you see like the circumferential part is coming. And if I am talking about like the previous figure, then we have like taken out the small piece of a cylindrical wall, and also you see, since this piece is symmetric towards all the direction r theta z direction, so we can easily show the r theta z stress components all across like in the this front side and the back side of these small segment. So now you see, if I am talking about like this kind of the pressure exertion on this thin cylinder, then you see there is a type of failure can also be there, because we just want to limit our load condition. So if we go beyond the load condition, then as I told you that the kind of plastic deformation may occur. So we would like to like keep the load condition below certain level, and if we go, then actually what will happen, a type of you see like the ultimate tensile strength will come, because it is a tensile loading, and then it appears to be a fracture. So what type of failure can come if you see we go up to a certain level? Then you see such a component which like fails in the this kind of pressure vessels when subjected to an excessive high internal pressure, like always gives you a real feeling that it may fail towards in excessive force in this z direction, in the longitudinal one. It may fail towards the normal direction in the this rth direction, or it may fail due to the this more circumferential stresses, because stress is uniformly distributed, and you see if it just like pushing towards the outward direction, there is a fairly well chance to have an expansion in those direction, and there may be a fail. So you see here, if you are talking about the fail in this kind of thing, then you see all three like possible cases are there. While it might fail by bursting along the path following the like the circumference, as I told you, towards the z direction of this cylinder. Under the normal circumference, it fails by like the circumstances, it fails like the bursting along a path parallel to the axis, like as I told you the longitudinal one means the z direction. So this suggests that the hoop stresses is significantly higher than the axial stresses. So here you see like the new term will come as the hoop stresses. One is the longitudinal stresses, that means you see we have like the kind of hoop stresses, the technical term is there in the z direction. We have the lateral stresses, that means we have the circumferential stresses in the theta direction, as we discussed in the first point. So you see it can be burst in the circumferential one, it can be burst in the z direction, the hoop one. So here which stresses are like the dominating, it has to be like taken care of, and accordingly the factor of safety is to be considered just to safely design the kind of thin cylinder. So if you are talking about the application, then you see there are like the tons of applications are there where these thin cylinder walls are usable only, where the thickness by internal radius is always smaller than 0.1. So what the applications are? The applications are the liquid storage tank, where you see always like we are keeping all those the liquids, or which has a lower temperature, or we have the containers in which all these like the kind of steams which we can keep, or we are just using the water pipes. We have the boilers in which you see the steam is to be generated for power generation. So submarine hulls are there, which like always operating below like the water level. So the kind of hydrostatic pressures are there right from the external and the internal sides. These are the common components which like we are using, or generally like some of the airplanes are there, where the like the kind of drag forces are there right from outer side as well as the inner side. So we have to be designed safely that which forces are dominating in what direction, and if we are talking about the hoop, or if we are talking about the longitudinal this lateral one, then how we can design safely that, because you see if you are talking about the underwater or the air kind of situations are there, then the whatever the subject the pressure variation is there, it depends on where it is landing, or you see where it is like flowing, and what kind of drag forces are there, and how the lift forces are coming from these internal parts. So you see we have to be very careful if you want to design you see like the thin wall cylinder, and based on either the spherical one or the cylindrical one. So as we have seen that actually there are lots of applications for these kind of thin cylinders, where like all the kind of load or we can say the pressure variations are there. So now if you want to analyze those components, then for analysis, first of all we would like to make certain assumptions prior to analyze the kind of stresses, and because of the the kind of internal pressure, how these stresses formations are there and what kind of strains are there, and how we can make the relations in we can set up the relation between the stresses and strain. This kind of analysis which we are gonna discuss here. So here first of all certain assumptions prior to do the analysis. The first assumption is there are no shear stress acting in the wall. You see it's pretty simple that when we are talking about, let us say, a boiler, or if you are talking about a water pipe, the water is flowing or this steam is flowing in the boiler is in very streamlined manner. So you see wherever they are striking on the wall, they are always trying to go towards the outward direction. That means you see either we have a the compression or we have a extension. There is no shearing is there. That means you see whatever the force application is there, this is the point of force of application. That means the point of application of this kind of forces or the pressure on these outer surface is just normal to the surface concern. That means whatever the stresses are forming due to these loads are always the this normal stresses. There is no parallel forces, means whatever the layers are there of this particular thin cylinder, they are these forces are not exactly parallel to these layers. That means there is no shearing is there, and that also there is no eccentricity is there where the load application is there. So there is no chance where the shear stresses can be formed in a pressure vessel. So again you see we need to assume that this has to be uniform all across the this pressure vessel. So whatever the stresses are forming, they are always in the form of the normal stresses. No shear stress is there on a wall. So this is the first assumption. Second assumption is the longitudinal as well as the hoop stresses do not vary throughout the wall. That means you see there is no stress concentration is there all across the wall, and this wall is well this surface tuned is there. That means you see whatever the surface roughness is there, it is highly super finished. Even we can say the honing or lapping, whatever the processes are there, we need to apply to make the surface roughness perfectly, so that whatever the flow or this pressure is going on, it has to apply a uniform pressure. That means there is no variation of the pressure is there, and there is no displacement of the microstructures are there inside the wall, so that we have a different kind of pressure. So this pressure is uniformly distributed all across the body, irrespective of whether we are talking in an axial part or irrespective of whether we are talking about the longitudinal or we can say the circumferential part. So in the longitudinal and the hoop part, there is no change of the stresses if we are moving towards the wall thickness or if we are moving towards the outward direction. So you see here what we have, the next one is the radial stresses, this you see towards the circumferential direction, which acts normal to the curved plane, like the sigma r we are talking about of this isolated element are always negligible. That means you see because it is just we have a confined structure. So whatever the pressures are coming which are normal to the surfaces, always they are not in the dominating way as compared to the other two forces like the hoop or the longitudinal one. So you see if whatever the stress components are coming all across the curved plane, it can, for in this particular isolated element, it can be neglected because it is if it is less as comparable to the two other stress component, and the state of the stress for an element in this particular thin wall cylinder pressure is considered to be biaxial. As we discussed, you see it is always biaxial. One is along the x axis, one is along the y axis, or we can say along this particular normal to this x axis in x or y z. That means it is in the circumferential style. Although the internal pressure acting on the normal to normal to these kind of loads will cause, you see on the particular wall especially, a local compressive stresses which is exactly equal to the internal pressure. That means pretty simple. If we want to analyze any kind of the stress analysis and the corresponding strains, the deformation I should say, then always you see we need to consider the biaxial state of stress. That means you see one is along the x axis, one is along perpendicular to this axis in any of the direction, and both are playing an important role to carry out that how the interactions are there and what exactly the kind of deformation will come in the structure. Actually a state of triaxial stress exists on the inside of the vessel, but you see since we know that the one component which is the normal to this plane the sigma r is not dominating as compared to the other two surfaces like hoop or longitudinal one. So, that is what you see, like we are not going to analyze these pressure thin vessels on the basis of this triaxial part. So, biaxial state of stress will give you the sufficient knowledge for this kind of structures. However, for this thin walled or this thick walled structure, always the third stress is playing some sort of the key role where the less pressure analysis is there. That means you see where we are not going for like a use pressure, but if a use pressure is there, then all the stress tensor always play a key role, and all three all 9 components, or we can say all 3 mutually perpendicular directions with the using of all 9 components of the stress, 3 normal stress and 6 the shear stress component are considerable, and we need to be very careful that actually how these stresses are interacting to each other and how we can get the corresponding strains are there with those tensor stress. So, you see here we will find that actually like these are the certain assumptions which are really fruitful to make an analysis for a thin cylinder. So, now you see here as we move the thin cylinder which is subjected to the internal pressure as we discussed, now how we can make the analysis. So, when a thin wall cylinder which is subjected to internal pressure, 3 mutual like the perpendicular principal stresses are well set up within the cylindrical materials, and those stresses are nothing but first, as I told you, the circumferential one, that is the hoop one, means you see in the theta direction. So, as like the steam pressure is generated, they are always act towards the outward direction, and which will always create like the stresses, and these stresses are known as the circumferential stresses, or we can say the hoop stresses. So, the hoop stress is the main stress which is set up in like the thin cylinder just to resist the bursting effect of the applied pressure, and can be the most conveniently treated by considering the equilibrium of a cylinder, because when it is just applying on the circumferential part, or we can say the lateral part, always it just tend to move towards the outward direction. So, like it will just try to give an impact of the bursting on the wall of the thin cylinder. So, we need to consider that wherever you see it is going towards the outward direction, what will be the like the resisting effects are there against these bursting effects. So, whatever the stresses which are inducing those things, they are known as the hoop or the circumferential stresses, and always we are treating these stresses after the equilibrium, that okay, they are well set up on the circumference of these thin cylinder wall. So, it can be easily evaluated on that basis, and as we discussed, you see like that these are always coming on the circumferences. So, in the next figure you see we are going to show you that in the half of cylinder, that how these like the formation of these hoop stresses are coming on that particular like the upper part. So, the cylinder is subjected to the internal pressure as usual, and due to this particular internal pressure P on like the circumference on the circumference of this thin cylinder, these induced stresses are there, which are hoop stresses, lateral stresses, or you can say circumferential stresses. So, P is the internal pressure, D is the inside diameter. So, because you see now we are considering the diametrical way, L is the length which is the longitudinal part, and T is the thickness of wall, and since you see we have already like discussed that what will be the limiting conditions are there for like the thickness to consider the thin cylinder wall. So, now you see like this figure, this is the thin cylinder you see which has a thickness T, and you see the internal pressure is acting on this. So, if you just see like the elevation, then you will find that we have the only this portion, a circular portion you see, and this is the cutting section AA. If you just cut the section at AA, we have the half cylinder, and we would like to see that what kind of stresses are there which are inducing in this cylinder and in this cylinder, and then what the like the variation is there along the length of the cylinder. So, this is you see the direction of the pressure which is exerting on like just inside the wall thickness of the cylinder, and then you can find that you see just they are simply going towards the outward direction. So, we have a bursting effect on the wall. So, now due to that you see always we have a kind of resistances are there from the wall side, and then you see it will just going against the bursting effect due to this pressure, because this will like just going towards the outward direction. So, you see like if you cut this section here, we have like this side view. So, this is the side view of these things, where this is the entire length of like this thin cylinder wall, and now you can easily visualize that there are two main types of the stresses are one at this particular circumferences, or we can say like at this particular direction, or at this diametrical ways. They are not along the length, but along the diameter of that, and these stresses are the hoop stresses. So, these are the resultant of these things, and the projected area is along this part. Okay. So, this is the diameter is there, along which these stresses are acting on this particular wall, and this is the thickness T is there, like. So, if we look at, if you simply cut the portion on this particular like this thin cylinder, then you will find that we have like the two main types of the stresses, because radial stress component has a minimum contribution to the overall stresses. So, probably we can simply ignore this part. So, by considering the two major effect of the stresses, one is the hoop stress. So, hoop stress is all along the diameter. So, this is the diameter, and these are like the hoop stress direction, which is all along the circumference of this thin cylinder. And then you see we have the other portion, which is just the longitudinal way. So, what we have this longitudinal stresses just along the length of this thin cylinder. So, this is the longitudinal the stress directions are there, and this is the hoop stress directions are there. They are both mutually perpendicular. Only like just keep this thing in your mind, both stresses are just the form of normal stress component. So, whatever the strain or whatever like the other properties are coming, they will just come due to this normal stress component only. There is no shearing effect is there with that, because the loads are just perpendicular to the active plane. So, now you see the total force on one half of the cylinder owing to the internal pressure P, because the exerting pressure is P. So, it is nothing but P into this projected area. So, what we have P into D into L, okay, the total length. So, P into D into L is nothing but the total like the pressure which is exerting on the total force which is exerting on one half of the cylinder. So, this total resisting force owing to the hoop stresses along the diametrical is well set up within the cylindrical cell. So, like with those things, with the T thickness, we can simply say that 2, because you see it is a half. So, total is the double. So, 2 into sigma h, which is the hoop stresses, into L into T will give you the total force in the like this whole thin cylinder, which has the thickness T. L is the total length, and sigma h is the hoop stresses which are inducing due to this internal pressure P. So, now you see like we have both the force component, and because of this sigma h into L into T is the force on the 1/2, as I told you. So, we need to multiply 2, and if equating both of the forces, we have the real value of the sigma h, which is exerting in the thin cylindrical wall due to the internal pressure P. So, it is equals to 2 times of sigma h into L into T, which is equals to P into D into L, or we have a sigma h, which is the hoop stress or circumferential stress, or you can say the lateral stresses, is equals to P into D divided by 2T, or we can say that circumferential this is nothing but equals to PD by 2T. So, you see here the main contribution of sigma h is always along the circumferential, and in that the dominant parameters are first the internal pressure, because this is the main cause for any kind of stresses, that what the pressures are there, how they are exerting. Second is the diameter. If more diameter is there, more like this sigma h is there. But the important thing is that how the pressure variation is. If you keep on increasing the pressure, internal pressure, always the stresses, whatever the inducing stresses are there, they are always on the higher side. But the other thing is that it has a reciprocal relation with the thicknesses. So, now you see like sigma h is proportional to D, sigma h is proportional to 1 by T, and sigma h is proportional to P. So, now this is the one form of this stresses which are inducing in a cylinder, and that is the hoop stresses, which are always along the diameter, or we can say always along the circumference of the thin cylinder. Second, you see, which we discussed, is the longitudinal stress. Considering the now the effect of the same figure, you see now we are again going for the same figure, in which you see the cross sectional areas were like that way, half of the cylinder, and along the length you see we have the total length is L along longitudinal axis. So, the vessel could be considered to have the closed ends, always you see it is a closed end, and contain the fluid undergoes like a gauge pressure P. So, we have a positive pressure due to the steam or any kind of like the internal whatever the liquid or gases are there, and this pressure is exerted on this wall, whatever the like this thickness of T is there. Then the walls of the cylinder, will have a longitudinal stresses as well as the circumferential stresses. Circumferential stresses as we discussed is always along the diameter, longitudinal stresses are always along the length of that. So, you can see in this diagram that like we have a thin cylinder and this is the pressure is exerting on along this x axis, and due to that you see we have the load application. Due to this particular load application we have the sigma L, which is nothing but the longitudinal stresses which are inserting on this thin cylinder along the length of these beams. So, you see there is no meaning with the diameter, but we have a clear meaning at this particular entire length. So, if you visualize those figures, then you can easily say that we have both the component of the normal stresses and both are just normal to each other. That means both are mutually perpendicular, and that is why we can say that if one is along the length, other one is definitely along the diameter, and that is why you see the meaning is, if we are saying that one is along the length, it is the longitudinal stress, and other one definitely see along the diameter, or we can say the circumference, so it is the lateral stress. So, both stresses are exerting together when there is a fluid pressure P is there, which is exerting on the thin cylinder wall. So, now coming to the main point, that if we have a longitudinal like the pressures are there on the particular this axis, we have a longitudinal stresses, or we can say just along this x axis you see we have the stresses. So, the pressure into area will give you the force, that how much force is there, and since you see we are saying that it is a cylindrical portion is there on along this particular circumference and the total diameter is d. So, the projected area, or we can say the affected area by that is pi d square by 4. So, P into pi d square by 4, what P is the applied pressure which inside into pi d square by 4 will give you the total force. Now, you see this area of the metal which is resisting this force is along like these things, and we have the effective portion is the thickness T also be considerable in under that part. So, we have pi dt, where you see because the pi d is the circumference and this is multiplied by the wall thickness will give you the real feeling about that what is the affected part is under that particular force. So, this sigma L is nothing but our this longitudinal stress into D into T is the force in the one half of the cylinder, and this is you see and uniform in all across this particular this length of this particular beam, this thin cylinder. So, what we have sigma L into pi into D will be equal to the first equation which is coming the total force due to this applied force in the affected area P into pi d square by 4. So, if we equate both the things, then what we have a sigma L which is the longitudinal stress is nothing but equals to P d by 4T. So, if we compare the longitudinal stress and if we compare the circumferential stress at the same domain, then we find that the sigma L is like a half of the this sigma h. That means you see if you multiply sigma h by 1 of the half, then it is exactly equals to sigma L, and but the key feature is though it has a different magnitude altogether in the hoop as well as the longitudinal stresses, but the clear feeling is that the main inducing parameters, or we can say the dominating parameter in both of the stresses are same. That means you see the applied pressure, if you increase the pressure like the longitudinal as well as the circumferential stresses are increasing. At the same time, you see if you increase the diameter also, it has the same impact on the longitudinal as well as the circumferential stresses, and if you change the thickness also, it has a similar effect on the longitudinal as well as the circumferential stresses, only there is a change in the magnitude so. The meaning is that you see if you are changing any of the dimension, both of the normal stress component longitudinal as well as the circumferential will be affected simultaneously. And then you see we can say that if you want to consider the thin cylinder on that basis, always what we need to do, we need to correlate these two forms of the stresses, because you see it is only the normal stress components are there in these kind of stresses. So, in this lecture you see what we discussed, that if we have a thin cylinder, first of all we have to design the thin cylinder on the basis of their thickness, and then actually if any internal fluid pressure is there, then how we can say that these the three forms of the stresses are forming, then what exactly the relations are there in these particular stresses. So, we found that there are main three components of the stress formations are there in the thin cylinder. One is the radial, one is the longitudinal, and one is along the circumference. But the circumferential and the longitudinal are always dominating in the thin cylinder, but radial component, though it shows its presence, but it has a like the contribution is pretty small as compared to both of that. And then you see like we calculated that what will be the hoop stresses are there along the diameter of the thin cylinder, and we found that it is nothing but equals to PD by 2T. And then you see we also discussed about the longitudinal stresses, and also we found that it has the similar component which are there in the hoop stresses, only the change in the magnitude value is there, and it is nothing but equals to PD by 4T. So we can easily compare both of the terms in terms of the longitudinal as well as the circumferential stresses, but these are the individual part. So you see we must correlate that actually if the fluid pressure is there and both of the both you see the longitudinal as well as the circumferential stresses are there, then what is the correlation? And for that you see in the next lecture we are going to discuss about that like we have this longitudinal one, we have the mutually perpendicular this lateral one, and like if you refresh your ideas, then we discuss the Poisson ratio, because whatever the load application is there in this cylinder, again we are assuming that this is just under the this elastic deformation or this Hooke's law is valid. So for that you see the Poisson ratio is well defined for this reason. So if you include the Poisson ratio, you can easily correlate the longitudinal and the lateral ratio. Then you see you can say that whatever the changes are there in the length as well as in the diametrical side, we can easily correlate. So in the next chapter you see first we are going to discuss about we are going to discuss about how to relate these two dimensions, and then you see the most important part is coming, that when there is a change, a significant change is there, the length as well as the diameter, then what will be the net changes there in the volume. So this can be easily computed by the volumetric stress. So you see when we are talking about the stress component, then always there is a deformation is there, and to measure the deformation what we have the strain component, so volumetric strain is there. So in the next lecture you see we are also going to discuss about the volumetric changes, and then you see we can easily define the value of K, that is the bulk modulus of elasticity, that if you know the volume change and if you know the real volume, so whatever the changes are there in the volume which is computing the volumetric strain, we can also find out the value of the K, which is the bulk modulus of elasticity. And then you see once you know the volumetric strain also, then our main focus is there, that if we there is a change of whatever the pressure or whatever you see this these longitudinal as well as the circumferential stresses are there, then what exactly the impacts are there on these design of the thin cylinder. So for that what we are going to do here, we are simply designing that, okay, first of all you have this longitudinal stress and you have circumferential stresses, and then you are correlating with the Poisson ratio, and that also apart from that you have the volumetric strain. Then what? Then you see you need to define the principal stresses, you need to define the principal strain component, and then you see you need to find it out that, okay, we have both of them, means we have this longitudinal plane on the longitudinal as well as this lateral stresses are there on a simple this cubic form. Then how to analyze those components. So these all you see we are going to discuss in the next lecture. So just remember those formula for longitudinal stresses, and you see the circumferential stresses and what are the dominating parameters are there, and then what will be the the formulas are there for Poisson ratio mu, and what it has a clear impact just to calculate for whatever the deformation, or we can say the stress strain diagram, or we can say to measure the deformation. All those things will come because we are applying the load under the elastic deformation only, where the Hooke's law is valid. Thank you.